We have a small fluid here, a lump of fluid here, and we apply a force, or we can call it as a shear stress. Now this is the displacement from this point to this point. The fluid is displaced, and this is delta A, and this is the height of the fluid, and this is the small angle delta beta. Now this is the velocity profile, which is linear, and this is y, which is variable from this zero distance to this h. Okay, this is the total distance is h. Now we can say that what will be the relationship between this u by y and capital U and h. So capital U means the velocity at this point, at topmost point, capital U. And we know that this will be proportional, as this is linear, this will be proportional. U will be the velocity at any y, okay, which is a variable here, and this is U at h, at height h. Now we can write it as U is equal to U by capital U by h into y. Now from the figure we can say that tan beta is equal to delta A divided by h. Now this what happened to this fluid? There is a deformation delta beta, and it happened at a small time delta t. Now what happens is, when the delta t tends to 0, then delta t tends to 0, then this delta beta also will tend to 0. Now we can write this tan beta or tan delta beta as tan delta beta can be considered as delta beta only. Now we have the displacement here, so speed is equal to distance by time, so we can say this delta A displacement is equal to velocity u into delta t. Okay, now we can say that this delta beta is equal to, from here we can say that this is u delta t by h. Now we know the rate of shear strain is defined as, so I use a letter lambda dot. It is defined as delta beta divided by delta t. So we can define it in this way: this lambda dot is equal to, when delta t tends to 0, I can define this the strain rate in this way. So this rate of shear strain, lambda dot is equal to limit delta t tends to 0 delta beta divided by delta t. So this is equal to capital U by h from the previous expression. We know from Newton's law of viscosity, shear stress is directly proportional to shear strain lambda dot. Now we can say that this shear stress is directly proportional to this limit delta t tends to 0 delta b by delta t, or this is equal to capital U by h, and initially we have written that this is proportional to du by dy. So u by y we can call it as a small change du, and this y can be called as a small change, that is dy. Now using a constant of proportionality, tau can be given as, this is equal to, we can say that this is equal to, so this here we can call it as proportional. Okay, Now this is equal to mu du by dy, where this mu is called as dynamic viscosity. And the unit is, this is dynamic viscosity mu, and the unit is kilogram meter per second. And we can again define nu, which is kinematic viscosity, and this is defined as mu by rho, and the unit is meter square per second. Now we can say that this mu, so tau is equal to mu du by dy, and mu is actually tau divided by du by dy. From the equation we have tau is equal to mu du by dy, and this mu is equal to tau du by dy. Now whenever this quantity, that is velocity gradient du by dy, is lesser, then this quantity mu will be higher. And again, when this tau, the shear stress that we give, is higher, then also this mu is higher. So what is the physical meaning of this? Whenever we apply a stress here, there will be a velocity gradient which is linear, and the tau is more means the more is the resistance of this fluid to deform. Okay, so the mu is nothing but this is the physical property of the fluid, or this is an internal resistance of the fluid, which is its physical property to resist a change in stress, or which resist the stress applied on the fluid. Okay, so if the stress is more means the resistance of wood is more, the resistance of wood is more means the viscosity is more. And if the resistance is more, then whenever we apply a stress, then this velocity gradient will be lesser. Okay, it will the deformation, or the du by dy, will be lesser, then also this mu, the viscosity, will be higher.